measures of proportion and center. Example A, Tony ate 4 out of 16 slices of pizza. What proportion of the pizza did Tony eat? Express the answer A as a reduced fraction. What's 4 out of 16? And we can reduce that, divide top and bottom by 4, 1 over 4. As a decimal, well, we can actually do the division. A fraction bar is like a division bar. We interpret it as 1 divided by 4. 1 divided by 4 is 0.25. As a decimal, as a percent, percent means parts per 100, so we multiply the decimal by 100. So 0.25, multiply that by 100, that's equal to 25%. Okay, so proportions can be expressed either as a fraction, decimal, or percent, and they're always between 0 and 1. Example B, a poll showed that 44% of voters support Joe Biden. What proportion of voters support Joe Biden? Express the answer as A as a percent. Well, they already gave us it as a percent, 44%. As a decimal, percent means per 100, so it's 44 divided by 100. 40% is the same as 0.44. 44 divided by 100 is 0.44. And as a reduced fraction, well, it's 40%. We start with the percent if you want. 44% is 44 over 100 because percent is parts per 100. Divide top and bottom by 4 to reduce it, and it reduces to 11 over 25. So as a reduced fraction, it's 11 over 25. Example C, 60 patients out of a sample of 80 patients were cured by a new drug. What proportion of patients were cured? Express answer as a reduced fraction. Well, it's 60 over 80. And that reduces, if you divide top and bottom by 20, it reduces to 3 out of 4. Or as a decimal, well, if you actually divide, 3 divided by 4 or 60 divided by 80, 0.75. And as a percent is parts per 100, so we want to move the decimal point over 2 places, multiply by 100, or move the decimal 2 places, be 75%. Okay. Okay, example D, we have a sample of 10 birth weights in ounces, 103 ounces, 106 ounces, 48 ounces, 96 ounces, and so forth. Question 1, find the proportion of birth weights over 100 ounces. Well, first it will be helpful to arrange these in order from smallest to largest. So if we go from smallest to largest, we have 48, 85, 96, 98, 103, and so forth. And that makes it clear we can count the number of birth weights that are over 100 ounces. 1, 2, 3, 4, 5, 6. 6 out of 10 are over 100. As a reduced fraction, 6 over 10 p hat. By the way, sample proportions are represented by p with a hat on top, and it's usually pronounced p hat. 6 over 10, if we divide top and bottom by 2, it reduces to 3 over 5. As a decimal, well, we can divide. Fraction bar is like a division bar. We can do the division. 3 divided by 5 is 0.6. And as a percent, it's going to be multiplied by 100 because percents are parts per 100. It'd be 60%. Okay, so with numerical data, there's some other statistics we can compute. The mode would be the most frequently occurring birth weight, and there's 2 babies that weighed 104 ounces. So the mode is going to be the most frequently occurring birth weight is 104. And again, it helps to put these in order from smallest to largest. So the mode is 104 ounces. The median, if you have an odd number of data, the median would be the one in the middle. Here we have an even number. 10 is an even number. We have 10 birth weights. So it would be the average of the 2 in the middle. 10 divided by 2 is 5. So we count 5 from the bottom, 5 from the top. 1, 2, 3, 4, 5 from the bottom. 1, 2, 3, 4, 5 from the top. So the 2 in the middle are the 103 and 104. And we want to take the average of those two. So that means we do 103 plus 104 divided by 2. 207 divided by 2. 103.5 ounces. Okay. So the median 103.5. Mode and the median are all sort of measures of center. The median is more important than the mode. Probably the most important measures, two most important measures of center are the mean and the median. They're both very important. So I'm going to do the mean next. We've done the median. So the mean, sometimes it's called the average, but the mean is considered a more precise term. The mean, you want to compute it by adding up all the scores and dividing by the number of scores. And sometimes it's useful to have a formula for the mean. And the formula uses this Greek letter sigma, capital sigma, to mean sum. So this notation here means the sum as k goes from 1 to n. So we're going to use x1 to represent the first score, the first birth weight, x2 the second score, and so forth. The mean is represented by, sample mean is represented by x with a bar on top. It's called, we read it x bar. So here's the formula. It's going to be x bar is going to be the summation. Our sample size here is 10, but it goes up to whatever your sample size is. So in this case it's 10. So the summation as k goes from 1 to 10 of xk all over 10. So n here is going to be 10 because we have 10 babies. So it's going to be the first birth weight, x1 is the first birth weight, plus x2 is the second birth weight, plus x3, etc. And so we can put these in any order. You could do the original order, or you could do smallest to largest. I'm going to put them in the original order, but it doesn't matter. The order doesn't matter here for the mean. For the median, it's important. The order is important. You have to put it from smallest to largest. But for the mean, later we'll be doing a weighted mean, where the order is important for the weighted mean, but for the original mean, regular mean, it's not important. So 103 plus 106 plus 48 plus 96 plus 110 plus 98 plus 104 plus 85 plus 117 plus 104, and the whole thing is divided by 10 because we have 10 babies. So if we add these all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Add these up, it comes out to be 971, I think. It was 971 divided by 10. That's going to be 97.1 ounces. So the mean is 97.1. And so the mean and the median are both important. The mode is not used so much. There's some important theorems about the mean. There's a very strong relationship between the mean of a sample and the mean of the population. So that's one of the reasons that the mean is important. Okay, so another thing to sort of notice about any data set is whether there are outliers. And if we look at the data in order from smallest to largest, the outliers are more obvious. So there's the smallest number is 48, and the next smallest is 85. So there's a gap of about 37 between there, and that's actually a pretty big gap. From 85 to 96, there's a gap of 11. Here we have a gap of 2, 96 to 98. So and there's 110 to 117. There's a gap of 7, but anyway, the biggest gap here is from 48 to 85. There's a big difference between a 48-ounce baby and an 85-ounce baby. So probably just looking at the data, it appears that 48 is an outlier, what we call an outlier. And we'll have more precise ways of determining outliers later, but one way of determining them is just to look at the data and see if there's a number that's very different from the other numbers. So the 48 appears to be an outlier. And outliers are important to notice. For one thing, there might be typographical errors. So if a typographical error, probably you want to fix the error. It might be due to special circumstances, so it might be important to be aware of what the special circumstances might be. For this particular data set, it could be that the 48-ounce baby would have been a baby that was born prematurely, so that's important thing to know. It's also important to notice outliers because they might affect the statistics. The median is usually not affected by outliers, but the other and median is what's called a resistant statistic because it's usually not affected by outliers, but the other statistics are usually affected by outliers, or at least the ones that we've gone over so far. Just to illustrate the effect of an outlier on the statistics, let's suppose we replace the 48-ounce baby with an 85-ounce baby. So the new data set would be 85, 85, 96, 98, and so forth. And so it's going to have an effect on the mode. In this case, we'd have two modes. We have two babies of 85 ounces and two babies of 104 ounces. So before, with the original data set, we only had one mode of 104 ounces, but now we have two modes. So the outlier had an effect on the modes, but the median is going to be the same. We have 10 babies. If you count 5 from the smallest to largest, 1, 2, 3, 4, 5, you get the 103. 5 from the largest, 1, 2, 3, 4, 5, the 104. It's still the average of 103 and a 104, and it's going to be 103.5 ounces. The mean, so the median stays the same. The mean, if we add these up and divide by 10, it comes out to be 100.8 instead of 97.1. So the median was the only one that was not affected, and that's typical. Usually the median is not going to be affected by outliers. There's another measure of spread, another measure of center called the midrange. Again, this is not as important as the mean and the median. The mean and the median are the sort of the main measures of center, but the mid-range is the advantage of the mid-range is easy to compute. It's just the smallest plus the largest divided by 2. So using the original data, the smallest plus the largest would be 48 plus 117, and divide that by 2. That's going to be, I guess, 165. 165 divided by 2, and that's going to be 82.5. If we use the revised data, with the revised data, the smallest number is 85. So it'll be 85 plus 117 divided by 2. And that's going to be 202 divided by 2, which is 101 ounces. These are in ounces, both of them. The outlier has a big effect on the mid-range. So the outlier can have a big effect on either the mode, the mid-range, or the mean, but usually it does not affect the median. Okay, so I want to say a little bit about the relationship between statistics and parameters. So the statistics that come from a sample that's typically from a larger population. So, for example, in our sample, 60% of the 10 newborns weighed over 100 ounces, but we want to. What we'd like to know is the proportion of babies in the population of millions that would be over 100 ounces. So we want to know how confident we can be, so usually the population parameters are not known. So the sample proportion was 60%. The population proportion, that's represented by p hat. Population proportion is unknown, but our best guess as to the population proportion would be based on the sample. So if you're to use some of the other examples, if you were let's say in our sample of several thousand voters, the proportion favoring Biden was 40. Let's say it was 44%. We use that to. We don't really know the proportion favoring Biden in the entire population of millions. It would be expensive to ask everyone in the whole voting population what their preference was. So we use the number from the sample, but the sample proportion p hat would be the 44%, and the population proportion, proportion favoring Biden in the entire population is unknown, but it's represented by the letter P. Some books use the Greek letter theta. It's very common to use the Greek letters to represent the unknown population parameters. So the sample mean, x with a bar on top, or read that x bar, is an estimate for the unknown population mean, which is Greek letter mu. It looks like a U, but with a little extra tail there. Later we'll get into some other statistics. The standard deviation, a sample standard deviation S, is an estimate for the unknown population standard deviation, sigma, Greek letter lowercase sigma, correlation coefficient, sample correlation coefficient R, estimate for the unknown population correlation coefficient, Greek letter rho. But we'll get into more detail on some of this later. I think in 2 weeks we'll be studying measure the spread, which includes standard deviation, and then I think in week 6 we'll go over the correlation, and then starting in week 11 we'll start talking about the relationship between the sample statistics and the population parameters. Okay, so that concludes this presentation.